Today we have two speakers. We have Giovanni Di Fresco and Stefano Scali. We start with Giovanni Di Fresco. Giovanni did his bachelor and master in Palermo. He got his master degree in physics in March 2021 with a thesis on multi-parameter critical quantum metrology. And he is now doing his PhD, always in Palermo, in the topic of researching quantum mechanics and statistical physics, by studying many body systems focused on quantum critical phenomena. And he has interest on multi-parametric quantum metrology. He will give us a talk today on quantum sensing in the presence of measurement-induced phase transition. And please, Giovanni, the floor is yours.
Okay, I will start by sharing my screen. Can you?
Yes.
See it?
Yes, I see the screen. So please start.
Just.
Is it not full screen at the moment? Now it's full screen.
Okay, so before I start, I would like to thank the organizer of the event for letting me speak here today. And today I'm going to talk about quantum sensing in the presence of measurement-induced phase transitions. The talk is divided mainly in two parts. In the first one, I'm going to give a general introduction about quantum metrology and what measurement-induced phase transitions are. And in the second one, I'm going to show you some of our results. So let me try to convince you that doing quantum metrology with many body system near a critical point is quite interesting. And usually this research field is called quantum critical metrology. In order to do this, let me start by introducing what metrology is. So let's imagine that we do some experiment, and at this stage we don't really care about the nature of our physical system, but let's say that we do this experiment and we end up with usually we end up with a bunch of data. And what we want to do usually from this data is to find the estimation of some physical quantities that here we call theta tilde. In order to do this, we have to define a mathematical function that is called an estimator, and is this object here, theta hat. What theta hat does is that it takes an input the data and returns as output the estimation. A simple example can be, for example, the mean. Now, a question easily comes to mind, that is, okay, how good our estimation is, and is there a way to benchmark, right, this how good our estimation is? And the answer is yes. We can use something quite well-known bound that is called the camera bound. And basically what this bound does is that you can compute the variance of this estimator theta hat, that is basically the error with which you estimate this parameter theta tilde, and you can compare it with this object here, that is 1 over f, where f is the Fisher information that is defined only through the probability density function of your data. And basically, since this bound is, at least for this, in this framework, is tight, so you can always find at least asymptotically. So where asymptotically means that in the worst case scenario, you have to repeat your experiment an infinite amount of time. This bound is always tight. So basically what you can do is that, okay, I pick an estimator and I compute its variance, and I see, check how close I am to 1 over f. And usually what you want to do is that you want to go as close as possible, obviously. Now, let's now focus on having a quantum system as our physical system. Let's see how we can exploit quantum properties of our system to enhance this estimation, the precision of our estimation. So, as I showed you in the previous slide, somehow the lower bound of this object depends on the probability density function of our data. And a very natural way that we have to change this probability density function when we deal with quantum system is by changing the measurement operators that we use to perform all the measurements. And if we basically optimize over all the measurement operators and also over all the estimators, we can find this well-known quantum Cramer bounds that basically is a lower bound than the one that I showed before, and links the variance of the estimator theta with this object that is called the quantum Fisher information that is defined in this way, and basically it depends on the density matrix of your system theta rho, and this object here L is an operator that is the solution of this equation here, and it's called symmetric logarithmic derivative. And if you're asking yourself if this bound is again tight, the answer is yes, when you want to estimate one single parameter, and the measurement operators that you have to choose to satisfy this bound are projective measurements on the eigenstates of the symmetric logarithmic derivative. So now that I introduced what quantum metrology is, so we can try to answer the question, okay, why it is interesting doing quantum metrology with many-body system, and especially it is interesting to do it near critical point. In order to do this, we can start to look into mainly the two ways in which you can build these metrological schemes. Basically, what you're interested in is how your density matrix somehow, how you encode the knowledge of your parameter in your density matrix. So in a first metrological schemes, what you can think of is, okay, I have basically my state rho, and you can think of having some quite general state. For example, you can generalize something that works well for your experiment, and then you can somehow encode the knowledge of this parameter through a unitary operator in this way. And this is usually called the unitary rotation framework, or also interferometric approach. And it will be clear in a moment why it's called interferometric approach. So basically, let's focus now on the form of this object U. Basically, you can say, okay, I encode the dependence of the parameter in this way, and U usually has this expression here, where G is a single body, is usually a single body operator, and the parameter that you want to estimate is this phi here, and this is why is called interferometric, because I mean you are interested in estimating phases basically, and the reason why it is interesting to do quantum metrology with this scheme in mind is because it is possible to prove that if you compute the quantum Fisher information for a separable state rho, so if the state here is a separable state, independently on the operator G that you choose, the Fisher information can at most scale linearly in n, where n is the size of your many-body system, and also you can think of like the size of the many-body system as the amount of resources that you put in your metrological scheme. Then by having this bound, the Fisher information can scale at most linearly in n, basically you have no advantage in having like a quantum system. You are like, by incrementing the amount of resources, you are incrementing like the estimation, like in any classical problem. But you can show that if you take a general state rho, then you can have that the Fisher information can grow super extensively in the size of your system, and this is mainly due to the fact that your state now it's entangled, and also you basically show that there is metrological useful entanglement, because if this object F scales super extensively in n, then you can perform very precise estimation of your parameter phi. And the maximum that you can obtain in the growing of F with respect to n, it's you can find out by looking at this chain of inequality that basically if you take a state that is K entangled, by computing this chain of inequalities that are mainly due to properties of the Fisher information, you can show that this object can scale at most as an n squared. And this is called Heisenberg limit, where when the Fisher information scales linearly, it's called Schottner's limit. So, in order to summarize, basically we have that, okay, we showed that the official information can be used as it is useful from a methodological point of view to do metrology when your state is entangled, but also from a many body point of view, it is interesting to use the quantum efficient information as a detecting tool to understand how your state behave, because it can be used as a detecting tools for entanglement. So basically, if f is proportional to n, independently on how you choose G, then your system is basically a product state. But if you find that G for which f has a super extensive scaling, then you find out that in your system there is metrologically useful entanglement, but also that your system is entangled, basically. And an interesting properties of f is that not only it is a witness of entanglement, but it is a witness of multipartite entanglement. So if you have that f over n is less than k, and k is a divisor of n, then in your system there is at least k plus 1 partite entanglement. Okay, so let's focus on the other methodological scheme that is usually used in this field, and basically you have here that rho, the parameter rho, the parameter gamma of your density matrix rho, you have to think in this case that they are somehow given by nature, for example. What I mean is that, for example, you are interested in studying the parameter, maybe in estimating the parameters, for example, of a Hamiltonian, and rho is, for example, the ground state of this Hamiltonian. And so you are trying to estimate, for example, gamma by changing a little bit gamma and see how the ground state of the Hamiltonian changes. And usually this is called like a adiabatic approach, because you think of doing this adiabatically, but you can use also more general dynamical properties, as for example quantities. Okay, so let's see why it is interesting, because okay, let's focus for a moment to equilibrium phase transition. So our phase transition that happens at t equals to 0, and we are interested in the ground state properties of many body systems. And you say, okay, I want to see how my state changes when I changes my parameter from gamma to gamma plus delta gamma. And this is, you can do this by computing this fidelity. And if you do like a Taylor expansion of gamma, you will find out this relation here. And the second order term is linked with something that is quite used in many body systems, that is called fidelity susceptibility. And basically, the reason why this object is quite used to study quantum phase transition is because if you imagine to do this procedure near a critical point, basically, if you change gamma, even of a tiny amount, delta gamma, if you cross the critical point, then this overlap is going to be 0, and you can realistically see from this relation that key should diverge, and usually key diverges super extensively in the system size. And the interesting aspect from a methodological point of view is that you can show that key is basically the quantum efficient information. There is a factor 4 of difference, and so if you try to estimate, for example, this kind of parameter, if you go really close to a critical point, you can get you can basically get a very huge increase in the estimation performances. So let's now introduce what measurement-induced phase transition. Usually, we are interested not in equilibrium phase transitions, but on out of equilibrium, in a specific kind of out of equilibrium phase transition. And usually, when you study out of equilibrium phase transition, you are interested in studying, for example, the inequilibrium steady state of a system, of the Liouvillean properties of your system. And basically, you have in mind to work with open systems. So it's a system that is coupled to an environment and a drive. And basically, an interesting way, in my opinion, to introduce what measurement-induced phase transition is to think of the system like we are working with systems that are for which the open dynamics is well described by a linear master equation, and we can somehow think of we can somehow imagine somehow like describe the dynamics given by the linear master equation by imagining that our system is coupled to a measurement apparatus. And the environment is this like imaginary measurement apparatus. What the environment does is that it measures our system, but since we cannot access the information of the environment, so we have to like trash the outcomes of these measurements. And the way in which we can simulate these dynamics is to really compute the stochastic evolution of psi, since the evolution is stochastic due to the randomness of the measurements outcome. And this procedure is called an unraveling of the master equation. And basically, you can then average over all these trajectories. After the averaging, you will recover the mean dynamics given by the master equation. But a few years ago, people started to ask, okay, what we couple our system with real measurement operators, and then we can really collect each outcome of the measurements, and then we can really start to follow each trajectories and start to characterize them. We can ask, is the physics at the level of the single trajectory the same as the physics of the mean dynamics given by the master equation? And the answer is that if you look at quantities that are non-linear in the density matrix, then you can start to see difference between the two regimes. And basically, if you look at entanglement, you can see that that if you study the entanglement at the level of a single trajectory, then something interesting can happen. Is that if you change the coupling with your system and the measurement apparatus, the properties of the entanglement can abruptly change as you increase the coupling. And let's pick a model and see what happens. For example, we can start to think of having a Tesla's Ising chain with a Tesla's magnetic field here, and you start to measure if each spin is in the apoptosis state. And for simplicity, we can work in a regime in which basically a click never occurred, so we never registered a click. And in this, we can do this by doing some post selection, and this is called the no-click limit. And basically, this is interesting because in this regime, we can describe the dynamics of our open system by looking at an emission effective Hamiltonian, that in this case is given by this Hamiltonian here. And so, basically, by studying the properties of this Hamiltonian, we can see the properties of our model. And if you look at the entanglement, basically you can ask, for example, what is the entanglement between a subpart of your chain and the rest of your chain, and you can compute this by looking at the entanglement entropy. That is basically the von Neumann entropy of the subsystem A. And this is, for example, the quantity that is usually used in literature to identify this entanglement phase transition. And basically, if you are below this critical value gamma c, you will see that the entanglement entropy scales logarithmically with n. And if gamma is greater than gamma critical, you will see that the entanglement entropy is constant with respect to the size. If you're interested in this result, you can find it in this nice paper here. But we asked ourselves, okay, can we use the Fisher information to describe this measurement-induced phase transition? Because again, quantum Fisher information is something that is non-linear in the density matrix, as you can see from here. And this object should be able to describe this measurement-induced phase transition because it is again something that can be sensitive, can be used as an entanglement witness when you do the first approach that I showed you before. And also we are interested in see, okay, how the susceptibility behaves when we go near this critical point. So when we look into the first approach, we choose as a generator of the unitary rotation this Sx, and we look into the scaling of the feature information. So you can see from here that if you are below this critical point, basically the feature information scales super extensively in the size of your system. And if for this point, from this red point here, you can see also that the scaling is proportional to 1.5, and this and then what this means is that in your system there is a huge amount of multipartite entanglement. That is something that you cannot see from the entanglement entropy because it only measures bipartite entanglement. When you reach the critical point and you cross it, the scaling abruptly becomes extensive in the sides of the system. And then somehow with looking into the feature information, you can reconstruct the phase diagram of the system. In the other scenario that we are interested in is, okay, let's start by picking the ground state of the Ising chain. Let's imagine to somehow turn on our measurement apparatus. And so the dynamics is given by the quench of this non-emission effective Hamiltonian and a normalization factor to normalize our state. We are interested in computing, for example, the long time behavior of this object due to the fact that this becomes the steady state of the non-emission effective Hamiltonian. The feature information can be computed analytically for this system, and if you look at the definition is this, you can manage to find what is the expression of the derivative of the state. And basically, once you do a little bit of math with this object, you end up showing that the feature information is proportional to the covariance of this operator here, that is this time-dependent operator. And basically, you can plot the feature information once you find its analytical expression, and has these nice properties that diverge exponentially in time, and also for small time as this transient behavior, then the exponential scaling kicks in. But we are interested in studying how the feature information behaves when we go near the critical point, and if it has some non-analysis due to the phase transition. So what we did is that in the long time behavior, we managed to factor out this exponential scaling that is perfectly analytical in gamma, and we defined an auxiliary function that contains all the non-analysis of f with respect to gamma. And we studied its behavior, and we showed that when gamma goes to gamma critical, basically there is this divergence of the feature information here. And an interesting properties of this fidelity susceptibility is that if you look at the critical mode and how it diverges, basically you see that it diverges with two different power laws. If you go to the critical point with gamma greater than gamma critical, or if you go to the critical point with gamma lower than gamma critical, and so you have these two different power laws. And this is due to the fact that the energy corresponding to the critical mode, when you are below, when you are above gamma critical, it's purely imaginary, and it's real when you are below the critical point. And you can see from this inset here that the lines are the analytical prediction, and the dots are the numerical one. So to conclude, to summarize, we showed that the quantum feature information can be an interesting quantity to use to characterize measurement-induced phase transitions, especially because due to the fact that it can highlight multipartite entanglement, can tell you something more than what does simply the entanglement entropy. And also it highlights metrological useful entanglement, so you can start to think of some metrological purpose to you to exploit this phenomenon. And then we managed to show that also for this kind of phase transition, the fidelity susceptibility is divergent at the critical point, that it's something that can be useful to know but to characterize the universality class, for example, of this kind of phenomenon. Thank you for your attention.
Thank you. Thank you very much for the talk, Giovanni. Are there questions or comments? I have one question. You use the term useful and non-useful entanglement. Can you say more? I mean, what are the aspects of useful and non-useful, and what is the type of non-usefulness?
Yeah, basically, when you have the way in which you can use the quantum Fisher information as a witness of entanglement is that you have a state rho, right? And then if you find that pick the rho, so choose a rho and pick to 1G, if the quantum Fisher information diverges super extensively in N, then you are sure that there is an entanglement in your system. But you can find other Gs for which the Fisher information cannot scale super extensively. So your state is entangled, but the Fisher information scales linearly. So basically, if you want to use that state to estimate this phi, you will not have an advantage, right, in using the quantum properties of that state.
I see. Other questions or comments? But can you use also the term useful in the sense that you know, in some practical idea or situation, even idealized situation, you have let's say a better control or a better understanding of the system?
Yes, I mean, okay, yes. Basically, what you can do is I think that this idea is given by the choose of G, right? Because what the entanglement is sensible for depends on G and the operators that you use.
Okay, thank you. Any other question? So if not, let's thank again Giovanni